Hello, everyone. I would like to welcome you to the presentation of our capstone project, the Wireless Smart Junctional Tourniquet for Continuous Blood Pressure Monitoring. My name is Sydney, and today I'm here with my teammates Logan, Camille, and Rachel. To begin, we have our full poster. This will be available in full at the CSU eDays website. However, for your convenience, we'll be going through it now step by step. To begin, we'd like to give you some background on how this project came to be. Many of us were involved in the Clinical Immersion Summer Internship Program in the summer of 2020. During this program, we had the opportunity to hear a talk by former combat medic Damian Berg. And in his presentation, he showed us a picture of a junctional tourniquet that would be used in a combat situation. We saw this idea and thought that there's certainly a way that it could be improved. So we proposed an idea at the end of the semester or at the end of the internship, and our idea was picked up. So one of the main things that Mr. Berg talked about in his presentation was that hemorrhage is a huge deal on the battlefield and is one of the major causes of death. And another very uncertain thing is that a lot of the times when these soldiers are brought into hospitals, their condition is relatively unknown other than their obvious physical injuries, but there isn't a great sense of what's happened internally. Therefore, through talking to Mr. Berg, a trauma surgeon, and a nurse with a vast experience with hemorrhage, we learned that the two things that would be most helpful to our clinicians is if they had a timer on each tourniquet patient so they can estimate the degree of damage within them, and also if they could get a continuous history of their blood pressure. This would help show any signs of crashing or any other issues that might help them make those split-second decisions when they come into the hospital regarding their care and care path. So although no one in our group had extensive experience with Arduino and Arduino language coding, we knew that this project would have the greatest clinical impact of any of our other ideas we had thought through. So therefore, we thought of it as a worthy endeavor to undertake for our senior capstone project.
So when designing the WSJT, there were four constraints that we wanted to meet. All of these constraints are primarily having to do with the additional hardware component rather than the junctional tourniquet as a whole. So with that being said, the first and probably the most important constraint was weight. Our goal was to keep our component under 200 grams, which was roughly the size of two small apples. Additionally, we wanted to keep the application of our device under 20 seconds. So that included applying both of the pulse sensors to the ear and to the finger, and then also pressing the button to start the timer and the blood pressure monitoring. We also wanted to ensure that the cost of the overall device was under $250. This included the ABS 3D printing materials and the Arduino kit. Lastly, we wanted to keep the compartment size under 150 cubic centimeters, which is slightly bigger than the Arduino Uno and the battery. So as you can see by this table, we were able to meet most of those constraints, except for the compartment size. Upon building the Arduino circuit, we realized that we needed additional space for the power strip. However, the size was still compatible with the WSJT, as it was about the same size as the width of the SAM junctional tourniquet belt, as you will see in our demonstration now.
Hello everyone, and welcome to the demonstration video for the Wireless Smart Junctional Tourniquet. To begin, we have our electronics housing here. If we open this up, we see inside that all of our electronics are nice and compact. This makes for easy battery removal and replacement. Upon replacing this, you'll also see that we have a few screw holes to better secure it. However, those aren't shown in this video. So to begin, we first take our finger PPG sensor. We're going to take the sensor portion and place it against the pad of Camille's right index finger. I'm pressing firmly so that there's good contact between the skin and the sensor and wrapping the Velcro tightly. Once that's placed, we're going to take our ear clip sensor. I'm going to open the clip, and the sensor portion will be firmly placed against the anterior portion of her earlobe. Once again, we firmly press on that clip to ensure good contact. Once both sensors are placed and stable, we come over to the exterior plunger, press firmly once, you'll feel the button depress and then come back up. Once this happens, data is immediately recording in our Arduino and can be transferred to any Bluetooth-enabled device as soon as the device connects to our Bluetooth module. This is great for paramedics or other clinicians in transport with the patient, and also allows clinicians immediate access to the patient's timer and blood pressure history upon arrival to the hospital. Thank you for watching our demonstration.
All right, so now that we have a little bit better idea of how the device actually works, I'll talk about the physical construction. So the device has been designed to be completely self-contained, and the clip design can be easily altered so that it can be used with any junctional tourniquet currently on the market. It consists of an outer enclosure made of ABS plastic, which was printed on a melt extrusion printer. The enclosure has a space for the external PPG sensors to leave the case, as well as a hole for an external button and screw holes for fixation of the lid. Inside the case, the main computational unit is an Arduino Uno, which is connected to a momentary button, which is acting as a switch, as well as a PPG sensors and an HM10 Bluetooth module. There is also a 2-channel breadboard that is used for power and grounding, which is connected to multiple circuits, as well as the 9-volt battery, which is the primary power source for the device.
So the software for this project was created in Arduino IDE using C++ coding language. 2 PPG sensors provided the input for this code, and then the calculation was started when the button on the electronics box was pressed. For both pulse waves, the peak values and times were found within a 1-second period. Then the time difference from one wave's peak to the other wave's peak was found to give you the pulse transit time. This time was then averaged within the 1-second period to help account for data variation and noise. The average was plugged into the model equations to give the systolic and diastolic blood pressures. While this was going on, the timer that is built into the Arduino was used to give the time since application every single time the code ran through the blood pressure calculation. Then both the time and the systolic and diastolic blood pressures were outputted to the connected phone over Bluetooth to give continuous patient monitoring.
For validation of the structural integrity of our design, there were a couple of different tests that we ended up running. So first, before constructing the device at all, we ran a finite element analysis simulation where we applied a force of 556.03 newtons, which was distributed evenly across the lid of the device. In that simulation, the maximum stress was found to be 15.7 megapascals, which occurred at the top lid edge interface of the device, where you can kind of see that red region in the image to the right. We also performed an in-person compression test where the maximum stress that was reached was 56.9 kilopascals before we saw any delamination, at which point the test was stopped. And that was carried out with a circular compression system that did not distribute the load completely evenly across the top of the device, but still managed to apply a load of 1,026 newtons before that failure was observed. Both of these results are well within the constraints for the device.
In order to find model equations that related the pulse transit time to the blood pressure, calibration testing needed to be conducted on our system. So we did testing using the PPG sensors and a blood pressure cuff simultaneously to give both the pulse transit time and also the systolic and diastolic blood pressures. This was completed a total of 13 times on 4 different individuals that were in a resting state. This data was then inputted into MATLAB to do the model fitting. So we used the method of linear least squares regression in order to fit the data to a linear line and find the model parameters. Once we had both of these equations, they were then added into the Arduino codes so that we could calculate the systolic and diastolic blood pressures from that pulse transit time.
Using the method Rachel just described to calibrate the device, we also then did our testing. After we completed testing, we ran 2 paired 2-sided t-tests on both the systolic and diastolic blood pressure values. From this testing method, we got 2 p-values of greater than 0.05, where 0.05 was found using our confidence interval. And we were able to draw the conclusion from these p-values that the measurements between the WSJT and the partially available blood pressure cuff were not significantly different.
So in conclusion, our team was able to design the wireless smart junctional tourniquet. This was an additional device that was clipped onto the SAM junctional tourniquet, and it was able to successfully record time and blood pressure on a patient for about 6 hours and transmit that data via Bluetooth to an Arduino application on your phone or a computer. In the future, we would like to make the compartment housing waterproof to be able to withstand different types of environments. Additionally, inside the compartment, we would like to replace the Arduino Uno and the battery and the power strip with a smaller microchip to overall reduce the weight and size of the electronics compartment. Then we would like to find or create a pulse sensor that is not impacted by sudden movements or changes in breathing pattern. Once all these components are changed, we would like to do testing on a larger pool of subjects as we had to limit our pool of subjects due to COVID restrictions. As the Junctional Tourniquet team, we would like to thank everyone who supported us through this process of making the WSJT. We would especially like to thank our advisors, Matt Bertech and Damian Berg, for their insight and support of our creative process, and those who provided the funding for the Clinical Immersion Grant. Should you have any further questions or comments about the WSJT, please feel free to contact any one of our team members through these emails that are listed. Thank you for listening to our presentation and have a great day.